Good morning, students. In the last class, we have studied about the 555 timer block diagram. So, in today's class, we are going to see the application of this 555 timer. So, we are going to discuss about how this 555 timer is going to act as a astable multivibrator. So, what is astable multivibrator? So, astable multivibrator is a circuit which is going to generate a square wave, nothing but which is going to produce an oscillations such that it is going to oscillate between two different voltage levels, that is high level and low level. So in such a way, this astable multivibrator is going to produce a square waveform. So here you can see a square waveform. So that is going to oscillate between two levels, that is a high level and as well as a low level. So here you can see high level and low level. So now we are going to design a stable multivibrator with our 555 timer IC. So that is how we are going to see now. So this is the circuit for a stable multivibrator using 555 timer. So see here. So what we have done for this, so you can observe here, as we have discussed in our last class, that 8th pin of the 555 timer is connected to the supply, that is VCC, and first pin is connected to the ground. So see here, so we have connected 8th pin to the supply voltage and first pin to the ground. And as we have discussed here, the 4th pin is nothing but the reset pin. So if we are not using this reset pin, then what we have to do? So we have to connect that resetter, that is the resetter. We have to connect this resetter pin to the VCC. So when we are connecting this reset pin to VCC, it will not reset. So we have to make it high in all conditions. So next thing is we are going to take the output across the third pin, as we have discussed in our last class. So we are going to consider the output from the third pin, and here the fifth pin is a control voltage. So we are making this control voltage which is connected to the ground to a capacitor. To a capacitor, we are making it grounded. And then, so what are the pins we are going to consider here? The mainly for this the 555 timer to act as an stable multivibrator. So we are going to take externally 2 resistors and 1 capacitor. So these 2 resistors and capacitors plays a major role in producing a stable, that is in producing the square waveform, output square waveform. So what happening here? So we are going to connect a resistor R1 between the 8th pin and the 7th pin. So as we know that the 7th pin is nothing but a discharge pin. So here the 7th pin is the discharge pin, and 2 and 6 will make it short. So 2, that is a trigger, and 6 is a threshold. So we are making a short of these 2 terminals and connected through R2 resistor. And then we are making ground of these two pins to a capacitor. So these three components plays a major role in producing a square waveform. So we are going to see the internal, okay, the internal uh, block diagram of this astable multivibrator, and I'm going to explain that. So now you can see in this slide, so you can see that. So this is the internal block diagram of a stable multivibrator. Here you can see this is the internal block diagram of a stable multivibrator, in which so eighth pin is connected to VCC, and here you can see this is the reset pin connected to VCC, and R1 is connected to VCC, and here this is the pin number 7. This is the pin number 7. From pin number 7 to 6 we are getting R2 connected, and 6 to is shorted, and then see, this is nothing but the dotted portion is nothing but the internal diagram of our 555 timer. Now we are going to observe that how this is going to make is going to produce a square waveform. So first, as we have discussed that these two are comparators. So this is having a threshold voltage levels, that is at this point we are having 2 by 3 VCC, and at this point we are having 1 by 3 VCC. So these two are comparators. One is inverting comparator and another one is non-inverting comparator. So see here, so coming to this comparator operation, so whenever, so we are giving the external pin is, that is nothing but inverting pin. So as a fixed voltage is nothing but 1 by 3 VCC, fixed voltage is nothing but there is a threshold voltage of this comparator is 1 by 3 VCC, which is connected to the non-inverting terminal. Then whenever this voltage is greater than the voltage at second pin, then the output of this comparator will be 1, and whenever the voltage at the second pin is less than this voltage, then the output will be 0. The output will be 0. Okay? Again, once again I am explaining that. So if a negative value is, for example, if the voltage at the inverting terminal is greater than non-inverting terminal, then output will be 0. The voltage at the non-inverting terminal is greater than inverting terminal, the output will be 1. Okay, in this way the two comparators will operate, whereas one is acting as inverting comparator and another one is acting as non-inverting comparators. Based upon this comparators operation only, this circuit is going to produce oscillations. Now we are going to see that. So initially we assume that the voltage across this capacitor is 0. Initially we are going to assume that the voltage across this capacitor is 0. So the voltage at this pin 2 as well as the voltage at this pin 6 is also 0. So 0 is connected to inverting terminal, and at non-inverting terminal it is having some voltage which is equal to 1 by 3 VCC. Okay, for example, if you take VCC is equal to 9 volts, then what happens? 3 is 9. The voltage at this terminal will be, so the voltage at this terminal will be 3 volts. I think what? 3 volts. So like that. Okay. So 3 is greater than 0 because the positive is greater than negative, because this terminal is 0. So as the positive is having highest value, the output of this comparator is 1. The output of this comparator is 1. And coming to this operation, upper comparator operation, so see here, upper comparator, the positive terminal is having 0 volts, that is the non-inverting terminal of the above comparator is having 0 volts, and the inverting terminal is having 2 by 3 VCC. So for example, VCC is equal to 9, then what happens? 2 to the 6. Here we are having 6 volts. So 6 is greater than 0. So as inverting input is greater than non-inverting input, the output of this comparator will be 0. So 1 0. So as we have given this 1 2 flip flop, RS flip flop, and S value is 1 and R value is 0. So as we have discussed that when S is equal to 1 and R is equal to 0, then what happens? So when S is equal to 1, R is equal to 0, the flip flop is going to set. So when this flip flop is going to set, then what happens? Then what happens? Nothing but the flip flop. Options. Okay. The flip flop uh, is going to produce the output Q as 1 because S is 1, the Q will be 1, and when Q is 1, then Q bar is equal to 0. So the output of this will be 0, and this is applied to the output circuit that is nothing but an amplifier as well as inverter. So 0 is applied to the output stage which produces output as 1. That means whatever the Q is there, that will be the output here. So Q is 1, then output will be 1. So because here we are placing inverter, okay, the output is 1. Okay, the output will be 1 at this stage. So this is a stage 1 explanation. And then what happens next? Next, what happens means, so as this is 0, the output will be 1. So as this is 0, nothing will happen. So now, so what happens as the capacitor is not having any charge? Now, by switching on this, the capacitor is going to acquire charge. The capacitor is going to acquire charge. So through this path, you can see the capacitor is going to acquire the charge through this path. So now from VCC, the capacitor is going to getting charged. That means from 0 level, it is going to charge towards what? Towards VCC. So now it is going to acquire charge from 0, 0 to 1, 1, 2, like that. It is going up to VCC. Let us consider this VCC as 9 means. So from 0 to 9, it is going to charge slowly through the resistors R1 and R2. The charging time period depends upon this R1 and R2. The charging time period is going to depend upon R1 and R2 values. So now capacitor is going to charge. So what happens then when capacitor is going to charge? Okay. So here we are getting a voltage. So here we are getting a voltage that is going to increase. So when this negative, that is inverting terminal, acquires highest value than non-inverting terminal, because the voltage at this node is fixed voltage, that is 1 by 3 VCC, whereas the voltage across this capacitor is going to change because the capacitor is going to charge. Now the capacitor is going to charge towards VCC. So whenever the voltage across this capacitor exceeds 1 by 3 VCC, then output of this comparator is going to become 0. The output of this comparator is going to become 0 because the potential at the non-inverting terminal is dominating, that is greater than potential at non-inverting terminal. This will be 0. So what happens to this comparator then? So what happens to this comparator? So this comparator, as this is acquiring, this is having maximum value. So as this is having maximum value, not below this voltage only, because the non-inverting voltage will be having non-inverting terminal will be having maximum value. Non-inverting terminal is having the maximum value. Then output of this comparator will be 0. The output of this comparator will be also 0. So when both comparators values are zeros, so these two zeros are applied to this RS flip flop, then what happens when 0, 0 is applied to an RS flip flop, then there will be a state that is no change state. So whatever the previous output is, they will be having the same thing. So the output remains 0, that is Q is 1 and Q bar will be 0. So Q bar is 0 means the output is going to remain at one state. So the Q is at one state, high state only. So the Q is at high state only. So next what happens? After that, the capacitor is going to acquire charge. So whenever the voltage at this pin number 6 is greater than the voltage at this inverting terminal of upper comparator, then the upper comparator output is going to change. The upper comparator output is going to change from 0 to 1. The upper comparator output is going to change from 0 to 1 state. So whenever it becomes 1, so that 1 will be applied to the flip-flop, reset terminal of the flip-flop. So when S is 0 and R is 1, then flip-flop is going to produce output which is equal to 0. The output which is equal to 0, that is Q is equal to 0 and Q bar is equal to 1. Now the Q bar will be 1. So when this is 1, then output is an inverter which is going to convert this 1 into 0. So here you can see the output is going to change its state from high level to low level, because up to now the output is at high level. Now it is going from high level to low level. So the output will be 0. The output will be 0. And at the same time, the output will be 0. So next, one thing you have to observe here. So Q bar is, now the Q bar is 1. So when Q bar is 1, so this 1 is applied to the base of this transistor. See here, the base of this transistor. When this Q bar becomes 1, so what happens? This transistor is going to on state. So this transistor is going to on state. So when this transistor is on, so what happens? It is nothing but it is going to act as a switch, so which is going to make ground. See here, it is connected to the ground. So whatever the charge acquired by this capacitor up to now will be discharged through this transistor. So now what happens? Up to now the capacitor is going to acquire charge. After getting this, the capacitor is going to discharge. The capacitor is going to discharge through the transistor, this transistor, that is through 7th pin. So this 7th pin is nothing but the discharge pin. Through the discharge pin, the capacitor is going to discharge in this part. So here you can observe the yellow line. So in this way, it is going to discharge its acquired charge to ground through the transistor. So now what happens? The capacitor is going to lose its charge. So what happens now? The capacitor is going to lose its charge. So when this capacitor is going to lose its charge, what happens? The voltage at this 2nd pin and 6th pin is going to change. You know that. The voltage at 2nd pin and 6th pin is going to change. Whenever the voltage at 6th pin is less than the inverting terminal, so whenever non-inverting terminal is less than the inverting terminal, then output becomes 0. Then output of this comparator becomes 0. So when 0, 0 condition is there, then the output will be 1. And what happens? The output will be in low state only. Again, the output remains in low state only. Okay. Next, the capacitor is going to discharge. Again and again. And when it discharges, so when the voltage across the capacitor is less than this lower comparator, coming to lower comparator state. So whenever the voltage across this capacitor is less than the voltage at this node, then what happens? This comparator output becomes 1. So when this becomes 1, what happens? When this becomes 1, so again the flip-flop is going to set. So the Q bar will be 0 and output is going to change its state. So in this way, so this 555 timer IC is going to produce a square wave. So the time period of this square wave is going to depend upon this charging and discharging of this capacitor and these resistors. Externally, what we are going to connect these resistors. So this is the operation of 555 astable multivibrator. So coming to the output waveform and capacitor waveform, here you can see the output waveform. This will be the yellow color waveform will be the output waveform produced by this 555 timer astable multivibrator, and then this is the charging and discharging of the capacitor. The blue color is the charging and discharging of the capacitor. So initially, so what we have is that initially the capacitor is having no charge. That is, the capacitor voltage across the capacitor is 0 volts. The voltage across the capacitor is 0 volts. So it starts from 0 and it is going to charge. So up to here. So after that, what happens? It is going to the output will be staying at 1 only, and after this point also the output is going to stay at 1 level only, because up to here the output is the comparator. You can observe here up to here the comparator output will be, the upper comparator and lower comparator output will be that is high reset state. The reset state will be there, and then after that no change state. In no change state it will be there, and then after that here it is going to set. So when it is going to set, when it acquires 2 by 3 VCC, when the capacitor voltage is equal to 2 by 3 or greater than 2 by 3 VCC, then it is going to change its state. Output is going to change its state. So after that, after changing the state, then what happens? The transistor is going to become on, and the capacitor is going to discharge. The capacitor is going to discharge now. So the capacitor is going to discharge in this way. So when the capacitor acquires the voltage which is less than 1 by 3 VCC, then again the output of the comparators is going to change their state, and then flip-flop state is going to change. Is going to produce again high value. So in this way, it is going to produce the output square waveform. So coming to the time period, so T1, so this is a charging time period, and T2 is the discharging time period. So T1 is given by 0.693 into R1 plus R2 into C. So why? Because here you can see when you are charging, so here you can see the capacitor is going to charge through R1 as well as R2. So because of this, we are going to write the equation in such a way T1 is equal to 0.693 R1 plus R2 into C. Okay, C. So what is this 0.693? We will discuss later in our time period explanation. I will discuss you about that 0.693. And then coming to T2, T2 is equal to 0.693 R2 into C. Here we are having only R2. Why? Because here you can see during discharge, so the capacitor is going to discharge through only R2. Here we are not, here it is not utilizing R1. So it is going to discharge through R2 and transistor. Not R1 is not involved in this. So because of this, T2 is equal to 0.693 R2 into C. So we can say that from this we can easily observe that R1 plus R2 is a very high resistance when compared to R2. Okay. So when resistance is high, the charging of the capacitor will be slow. Because of that only, the capacitor charges slowly. Because of that only, the time period T1 is more when compared with time period T2. So here only R2, because only R2, so the discharging through R2, so only having only R2 resistance, which is very low when compared to R1 plus R2. So because of that, the discharging time period is low. So here you can see, so it is asymmetrical waveform. That means the time period T1 is not equal to T2. So this is the multivibrator, a stable multivibrator, is going to generate a square wave which is asymmetrical, not a symmetrical waveform. So total time period, if you consider, that is T1 is equal to, that is T1 plus T2. So which is equal to 0.693 into R1 plus 2R2 into C. Because 0.693 into R1 plus R2 into C, so which becomes 0.693 into R1 plus 2R2 into C. So if you consider duty cycle, so what is duty cycle? Duty cycle is nothing but the on period, that is on time period divided by total time period. So here on time period is nothing but T1 divided by total time period is nothing but T. So T1 divided by T. So T1 is equal to 0.693 R1 plus R2 into C. So we have written that. And T2, T1 plus T2, 0.693 into R1 plus 2RC into T. We have written that. So CC will get cancelled, 0.693 and 0.693 will get cancelled, and we are having only R1 plus R2 divided by R1 plus 2R2. So that's the duty cycle. The duty cycle is going to depend upon the resistance values R1 plus R2 and R1 divided by R1 plus 2R2. So this is how okay. But as we know that in some applications, so we may need to generate a square law which is having uh, which is having same time period, that is on time period is equal to off time period. That is nothing but 50% duty cycle. That is nothing but 50% of its duty cycle. So for that we have to make that the charging time period of the capacitor equal to discharging time period. So for making that, here you can observe that we have to make that R1 plus this resistance must be equal to this resistance. That means T1 must be equal to T2. Okay. For that, we are going to consider the circuit, that is this circuit. So what we have observing here. So we are going to replace R1 with a variable resistor R1, and we are going to place a diode across in parallel, nothing but across or in parallel with R2. Diode in parallel with R2. So now what happens? What happens is nothing but so during charging. So here you can see the capacitor is going to acquire charge through R1, and during charging temperature, this is positive, this is plus VCC. So diode will be forward bias. So always we know that the current chooses the low resistance path. So see here, when charging, when it is going to charge, so it is going to charge through this path, that is through diode. So it is not utilizing the R2 during charging. It is not utilizing the R2 resistance. It is going to acquire the charge through R1 only. So R1 and diode resistance. As if we consider diode as an ideal diode, then what happens? So diode is having zero resistance. If we consider diode as an ideal resistor, ideal diode. So if it is a practical diode, it will be a few ohms, few hundred ohms, around few hundred ohms only. So it is very small resistance. So we can acquire a 50% duty cycle. So here only R1 we are going to consider, and during discharging only R2 we are going to consider. If we make R1 is equal to R2, if we make R1 is equal to R2, as R2 we are going to consider a fixed resistor, then if this variable resistor will be made such that this resistance is equal to this resistance, then we can produce a 50% duty cycle. Then we can produce a 50% duty cycle. So this is how the capacitor is going to acquire charge. The yellow line shows the charging path, and the green line shows the discharging path. So discharging will be done through R2, and charging will be done through R1 and diode. In this way, it is going to produce the output. So here what happens to T1 now? T1 is equal to 0.693 into R1 plus RD. RD is nothing but resistance. That is a diode resistance. Diode resistance, it is very small, we can neglect that. So RD into C. So T2 is equal to 0.693 into R2 into C. So if RD is equal to 0, then what happens? 0.693 R1 into C, 0.693 R2 into C. So then if R1 is equal to R2, then T1 is equal to T2, which produces a 50% duty cycle, which is going to produce a symmetrical square wave, which is going to produce a symmetrical square wave, which is having the positive time period, that is T1 is equal to T2. The positive, that is on time period, is equal to the off time period. Okay. So now coming to the duty cycle formula, we know that R1 divided by R1 plus R2. If R1 is equal to R2, if R1 is greater than R2, then duty cycle will be greater than 50%. If R1 is less than R2, then duty cycle is less than 50%. Because as we know that duty cycle is equal to on time period divided by total time period. So during on time period, R1 it is going to acquire the charge. The capacitor is going to acquire the charge through R1, and during off time period is going to discharge through R2. So this is total time period, that is R1 plus R2. So R1 divided by R1 plus R2. So this is how we are going to obtain the duty cycle of that is we are going to produce a symmetrical waveform. We are going to produce a symmetrical waveform using your 555 IC, 555 timer IC. Next, so we are going to design an astable multivibrator such that it is going to generate a 50% duty cycle and frequency of 10 kilohertz. He has given, so a problem is given for us. So it has to generate. It has to generate. So the values given is nothing but 50% duty cycle and the frequency must be 10 kilohertz. These are the two values given for us. And then with this we are going to design the R1 value, R2 value and the C value. R1 value, R2 value and C value. So that is how we are going to see. So for obtaining the time period, as we have seen the time period formula, that is T is equal to 0.693 into R1 plus R2 into C. So as we know that from this frequency, we can calculate the time period. That is F is equal to 1 by T and that is T is equal to 1 by F. So 1 by 10 kilohertz which is equal to 0.1 milliseconds. So T is equal to 0.1 milliseconds. 0.1 milliseconds is equal to 0.693 into R1 plus R2 into C. So we are assuming the C value here. We are assuming the C value. So assuming the C value as a 0.1 microfarad, 0.1 microfarad, then we are going to find the R1 value. So R1 plus R2 is equal to 0.1 millisecond divided by, so we are bringing this total 0.693 into 0.1 microfarad to this side. So it will become into the denominator. So then if you find the value, that is such that we are assuming that R1 is equal to R2. So if you find the value, then we are going to get the R1 value as 720 ohms. So R1 value is 720 ohms, R2 value is 720 ohms. Then C value is 0.1 microfarads. Then it is going to produce a square wave which is having duty cycle of 50% because R1 is equal to R2 is equal to R. So then, and having a frequency of 10 kilohertz and having a frequency of 10 kilohertz. In this way, we are going to produce a square wave of stable square wave using a stable multivibrator. So this is how we are going to design a multivibrator. Design a stable multivibrator. Next, so next we are going to discuss about how this 0.693 has came. We are going to observe now. So coming to our that is our waveform produced by our stable multivibrator. So here you can see the waveform. So when it is going to charge, acquire charge and discharge. So we are going to write that derivation for this the charging equation, which is given by the formula. We know that the formula. So the formula we are having here is nothing but so this is a formula. So that is Vc of t is equal to the capacitor charging voltage is equal to V final plus V initial minus V final into e power minus t by R dash into C. So we are assuming this R dash. So R dash is equal to R1 plus R2. Nothing but we are going to assume R1 plus R2 is equal to, in the place of R1 plus R2, we are going to place R dash. No, nothing difference in that. So in some textbooks we can observe that as we have observed this equation in PVC subject also in our linear wave shaping. Linear wave shaping, we are going to discuss about this formula. So voltage across the capacitor is given by V final minus V initial into e power t by RC into e power minus t by RC. So that may also be written as like this: V final plus V initial minus V final into e power minus t by RC. So here initial. So you see here initial value, initially the capacitor is going to start its voltage at this point, and finally it has to acquire the charge towards, so this is what VCC. So finally it is going to charge towards VCC. So initial is 1 by 3 VCC, and the final is VCC, and final is VCC. So V initial is equal to VCC by 3, and V final is equal to VCC. So we are going to place these values in this formula. So what happens? At time period T1, we are going to consider the charging time period, that is T1. So at time period T1, so T is equal to T1. So VC of T1 in the place of T, we are going to write T1 is equal to V final. V final is nothing but VCC. VCC plus V initial. VCC by 3 minus V final. VCC into E power. In the place of T, we are going to write T1. T1 divided by R dash into C. So by solving this equation, so 2 VCC by 3 is equal to VCC because VC of T1. So voltage VC of T1. So at this point, the voltage is nothing but 2 by 3 VCC. At this point, the voltage is nothing but 3 by 3 VCC at T1. VC of T1 is 2 by 3 VCC. So we are going to write this 2 by 3 VCC here. So 2 by 3 VCC is equal to VCC minus, so we are going to solve this, VCC minus VCC divided by 3, VCC minus 2 VCC divided by 3. So VCC minus 2 VCC divided by 3. Okay. So 2 VCC divided by 3 into E power minus T1 by R dash into C. So now by solving this, this, what happens? Minus VCC by 3 is equal to minus 2 VCC by 3 into E power minus T1 by R dash into C. So by bringing this 2 VCC by 3 this side, so or else we can cancel here because both are it is on LHS and it is on RHS. 3 will be get cancelled and VCC will be get cancelled, and minus will be get cancelled, and if we bring this 2 to this side, this becomes 1 by 2. So E power minus T1 by RC is equal to 1 by 2. So T1, if you take a natural logarithm on both sides, so T1 is equal to ln of 2 into ln of 2 into R dash into C. Okay. So if you take ln of 2 into R dash into C, so which is equal to ln of 2 value is nothing but which is equal to 0.693. So in the last slides we have seen that 0.693. So that 0.693 has came because of this 2, ln of 2, natural logarithmic of 2 value, that is a 0.693 into R dash into C. In the place of R dash, we have estimated R dash is equal to, that R dash is equal to R1 plus R2. So R dash is equal to R1 plus R2. So in this way, so we are going to acquire the time period T1. That is, we have observed the derivation for the charging time period of the capacitor. And then coming to the discharging time period. So during discharging time period, so the initial value of the capacitor will be 2 by 3 VCC, and the final value is nothing but it acquires 0, that is 0 volts. So finally 0 volts. So V initial is 2 by 3 VCC and V final is 0 volts. Same equation we are going to see here. VC of T is equal to V final plus V initial minus V final into E power minus T by R2 into C. Here, during discharge, we are having one resistor, that is R2. So we are going to consider only R2. So VC of T2. So because we are going to consider T2 time period, so V2 of T2 is equal to final value is 0 plus 2 by 3 VCC into minus 0 into E power minus T2 by RC. So by solving this, we are going to get the T2 value, that is equal to 0.693 into R2 into C. So this is how we are going to obtain the time periods for a stable multivibrator for both T1 value as well as T2 value. So the total time period which is equal to T1 plus T2. So the total time period T is equal to 0.693 into R1 plus 2R2 into C. So this is the astable multivibrator and derivations of this time periods, and as well as how we are going to generate the symmetrical wave from the symmetrical square wave using a stable multivibrator we have observed. So thank you, students.